Hello everyone, I am the presenter Zhihao from Shanghai Jiao Tong University. Let me introduce our paper about an interpretable deep reinforcement learning approach to autonomous driving. Autonomous driving is a hot but extremely hard technology. With the help of the development of different Jianyi simulators, deep reinforcement learning becomes popular in order to deal with the difficulty in collecting large-scale real data. However, due to the fact that almost all deep learning methods are not interpretable, so it's hard to position the problems, and also it's impossible to compromise with the ethics and laws. To achieve interpretability in autonomous driving, many researchers propose ideas regarding solutions of learning logic expressions, which can drastically decrease the degrees of freedom for humans to understand. Our work gives a similar approach to those solutions, which can provide simple logic programs to the autonomous driving problem after deep reinforcement learning, based on a novel neuro symbolic model, differentiable logic machine, so-called DLM. The data stored in DLM is categorized by arity. For each unit, the rows represent predicates. As illustrated, predicates in DLM is stored as truth values, indexed by full permutation of given objects. During training mode, the DLM treats them as numerical values with numerical calculations so that it can be differentiable. During evaluation mode, the DLM can degrade the units into several logic connections so that it can provide fully first-order logic solutions. DLM is constructed by multiple aligned layers. For each layer, they will receive the predicates from the previous layer and will output the results to the next layer. Each layer contains many units. In simple explanation, after the model converges, one unit will select several pairs of predicates from the previous layers and perform a logic connection out of 4 types: and, or, and not, and or not. The first layer receives the initial predicate directly provided by the environment, so we also need to transform the autonomous driving problem to adapt the restrictions. So the overall methodology is shown in the diagram, using the transform environment to train a DLM, and then extracting the larger solutions. We will discuss our practice about environment transformation combined with the experiments. The experimental environment we use is Highway N, a tactical decision-making task related to self-driving car. 2 scenarios, lane changing and intersection management, are used in our experiments. For the environment, we select a fixed number of social vehicles to be our input objects. The initial predicates will be related to common features such as speed, lanes, and so forth. For those discrete values, we can use one-hot encoding. For those continuous values, we can compare the values with thresholds. The action of the environment is in discrete action space, so it can be directly linked to the nullary predicates output by DLM. For the training process, we use PPO algorithm to train 3 models, which are neural network, LLM, and DLM. We haven't mentioned before, so LLM, the neural logic machine, is the basis of DLM, with almost the same structure without the capability of extracting larger programs. Here shows the training results. What to emphasize is that the comparison is not to show which model is better. Instead, it gives the evidence that DLM, with providing a larger solutions, doesn't sacrifice its performance. The logic program for the lane changing scenario is very simple. It gives the meaning that lane changing scenario itself is too simple with respect to the observations. Then if further targets are considered, we can follow the guidance to increase the difficulty in scenario. For the intersection management scenario, the logic expressions become much more complex. From the structure of the logic programs, we can conclude that the model gives 3 situations of deceleration operation, represented in P1, P2, and P3. We can also analyze each situation by checking the definition of the initial predicates. From above 2 experiments, we show the performance of our method in 2 scenarios in Highway N, and gives a brief explanation over the extracted rules. Since our work is close to application, so when considering the extensibility, there are some benefits and some drawbacks. Due to the property of DLM, the method can be extended to broader situations, which is remain to be proved by future works. Also, when applying to more complicated environment, extra efforts should be put on environment transformation and hyperparameter selection. Thanks for your attention, and if you are interested, referring to our article for specific details.